Okay, so now without further ado, onto the main part of this webinar. So over to you, Freya. So Freya is a climate scientist at the UK Climate Resilience team at the Met Office, and she's been in this role for about a year, but has been collaborating with the Met Office much longer through her PhD and other research. So her PhD was on the role of oceans in the climate system, but her current role is much more on the projections of future climate change, particularly multiple hazards, and what this means for sectors such as agriculture in the UK. And Freya is also passionate about science communication. Welcome, Freya, over to you.
Okay, thank you. Can you hear me and see the right slide okay?
Yes, we can see. That's great.
Great. Okay, so in this talk, I'm going to provide an overview of some of the compound events work I've been doing, so focusing on UK agriculture. First, I'm going to do an overview of our hazard to risk approach and a general introduction to multiple hazards. So a key part of our approach is not just understanding the climate hazards, but also thinking in terms of a risk-based framework. So effectively, we're drawing in the understanding of vulnerability and exposure to a hazard, which typically requires a sector-based understanding. So as such, we've really been trying to reach out and learn from people about the key questions and concerns that they have in their sectors. So what actually do I mean by a hazard? So the Cambridge Dictionary defines a hazard as something dangerous and likely to cause damage. However, regardless of impacts or likely risk, here we're actually considering any meteorological or Earth system variable that may change under climate change to be a potential climate hazard. So these are some of the ones most commonly considered in climate modelling. I'm only going to talk about the top 3 variables, so temperature, precipitation, and relative humidity today. So this infographic by the Met Office shows from the centre the drivers of climate change, and then the next layer, the changes to the climate system, so the climate hazard components. And then on the outer layer, you can see the impacts that we expect to see to UK sectors. So I'm going to talk about multiple hazards, when more than one climate hazard occurs at the same time, and more broadly, compound events, where a climate hazard can occur in close succession to another in terms of timing, or maybe widespread in its spatial extent. So this means that actually compound events could include any of the hazards or impacts on this diagram. So the diagram that we saw earlier, we can look at from a compound risk perspective. So as well as the climate events that may be extreme in multiple meteorological variables or compound in a temporal or a spatial sense, we know that in reality, compound risk is also going to be informed by non-climatic drivers as well. So I think it's really important that multidisciplinary research brings all this together. However, the compound events field of research is still fairly young, so initially my qualitative research will be characterising the projected changes in risk just from the climate hazards over the 21st century and assuming that non-climatic drivers remain constant. So I'm just going to mention the current COVID-19 pandemic as an example of a non-climatic hazard that can combine with extreme weather and climate events, triggering further severe impacts, such as we saw the delay of aid following a cyclone in the South Pacific. For an outline of how the pandemic, climate change and migration are interlinked, I recommend this webinar from Climate Outreach. It's a very apt cartoon here in the middle, which I was introduced to in a recent webinar for the Risk Knowledge Action Network for Compound Events. So that's worth looking up if you are interested more in compound events. So let's work through an example of a multiple climate hazard event and some of the impacts that there might be. and how these might cascade across different sectors of UK society. So say we have initially a period of very hot and dry weather. This might lead to wildfires and also decrease the quality and magnitude of crop yields. The wildfire and the high temperatures will both contribute to poor air quality due to increased particles in the atmosphere and heat transforming atmospheric pollutants and increasing toxicity. So in addition, high pressure in warm weather can increase the density of pollutants in cities. So high temperatures may lead to heat-related stress illnesses and mortality in a population. The poor air quality may also contribute to increased hospital admissions. So the high temperatures and droughts could also contribute to problems in the energy sector, as cooling capacity is reduced to substations and power transmission could be interrupted. So as the power is really important for providing a safe and clean water supply, then of course the water supply itself is restricted. So these energy sector and water sector impacts can then feed back on the wildfire, hospital and crop impacts as emergency responses are hindered and power and water supply is restricted. So of course the cost of energy and water then for farmers to try and water their crops in long drought can also restrict the use of water there. So the high temperatures could also contribute to the heat stress on livestock. This may lead to farmers having to keep livestock that usually graze outdoors, indoors, and that leads to additional pressure to feed them. So many interacting systems maps have been produced by WSP, and they're going to be a really comprehensive source of identifying possible cascading risk in UK sectors. So do keep an eye out for them when they are released later this year. So hopefully the example that I've just talked through demonstrates to you that compound events can be very complex. Firstly, in terms of their varying timescales, which could be extreme, instant, or prolonged over months. So I'm going to talk about two different cases of this today. So they may involve a very extreme or rare component, a so-called black swan event. But actually, compound events may just have severe impacts because of the combination of hazards and impacts, and the initial hazard may not seem particularly severe. The same climatic event may well hit multiple sectors simultaneously, and events in one sector, so for example the energy sector, could also trigger or amplify events in other sectors. So in this example, as power is disrupted. So this philosophy of Heraclitus, effectively you'll never step in the same river twice, applies really well to compound events. Compound events especially are highly likely to be unique with local impacts. So as such, more traditional methods of climate scientists, which are typically more large-scale assessments of risk, may not be ideal for local planners, and the science may be presented in a way that's difficult for planners to interpret or use. So we're going to focus on more local research and look at case studies. So as this philosophy indicates though, the lessons from a case study may not be broadly applicable, but our aim is that the methodologies that we are developing to examine future projections of multiple hazards will be. So we're going to build a publicly available code base, which at the end of the project, others will be able to use to look at other combinations of climate hazards. So to further comment on the stakeholder side of the project, what we've found so far across sectors is an acceptance of the likely growing importance of multiple hazards over the 21st century, but it's typically not quantified often by stakeholders. So the compound events field actually seems to me to be an intersection of several research communities. So the climate modelling community, the extreme events community, and the advanced statistical communities, as well as social scientists. So some sectors have practitioners with more understanding and experience in these areas than others. So the agricultural sector is considered to be a UK sector needing more action on climate-related risk. And so initially we focused in on multiple hazards in this area. But the idea is for us to develop case studies across a range of UK sectors during the lifetime of this SBF. So we are trying to engage with stakeholders themselves. So as well as producing interesting science, we're also focusing on creating products that are useful and usable by stakeholders and ensuring that we communicate in a way that's understandable. And coming from a climate research background, it has become clear to me just how hard it is to keep building and developing stakeholder relations and how time-consuming it can be. So a quick overview of the UK agricultural sector. The impact of extreme weather is already being felt by farmers. We've a mix of crops and livestock. Lots of outdoor grazing, sheep and cows, the meat from which are key exports from the UK. And the agricultural sector, of course, is a large employer, and it's particularly dependent on migrant workers. So here are some of the ways that we've tried to establish what are some of the key challenges for UK agriculture and how these might develop under climate change. So we've some experience in agriculture already within the Met Office, and we've built links into several different governmental type agencies who have more experience of developing science into policy. I've also found agricultural news to be a key source of understanding concerns, and now climate change is increasingly in the news agenda. So you have things like surveys which can give more information about farmer experiences. So our approach is to look at a number of case studies and create methodologies that can be applied elsewhere. So ideally with a range of case studies across the different climatic regions of the UK. So there's some thresholders or risk indicators that have already been established, and we can try and draw these into our own work. However, in some cases, we have to consider past compound events and generate our own thresholds for impacts to be able to assess changes in risk for similar types of events. So there are a number of different types of climate projections in the UK climate projections product, ranging from global projections using state-of-the-art high-resolution climate change simulations at 60-kilometre resolution to regional projections at 12-kilometre and 2.2-kilometre resolution. There are also probabilistic projections, which include much larger ensembles of a Hadley Centre model and information from CMIP5 models, but that is not spatially or temporally detailed like the regional projections. So I'm just going to take a couple of minutes to elaborate on uncertainty in future projections, which I hope will be useful to those listeners who might not come from a climate modelling background. So in fact, Richard Betts contacted me yesterday about the advertised title of this presentation. In the original, it actually had the words "will" in it. But of course, we can't exactly predict the future. We make climate projections, and to use them usefully, we have to understand the uncertainties within them. So for near-term projections, so within the next decade or so, internal variability, so the chaotic nature of the weather and climate, is the largest part of the uncertainty. A large ensemble of the same model with different initial conditions is a way that we can determine and try and estimate this uncertainty. And this is something that may be really important as well when you go down to modelling on very small regional spatial scales. So as you go out to multiple decades in the future, the model uncertainty becomes larger. So model uncertainty includes the parameters that we use to represent the subgrid scale processes. And we can estimate this contribution by varying these parameters in an ensemble. So this is what the global and regional projections in UKCRP do. So a multi-model ensemble then enables us to capture even more of the uncertainty. So the probabilistic projections from UKCP include a large HADCM3 ensemble and information from a CMIP5 multi-model ensemble. So towards the end of the century, the greenhouse gas emissions will have a much bigger contribution to the uncertainty in prediction. We capture this by considering different scenarios. So in the fifth assessment report for the IPCC, we had RCPs 2.6, 4.56 and 8.5. So these different scenarios are very strongly dependent on the socio-economic choices made over future years. So the climate response will vary depending on the path that we take, as well as the final outcome that might be expected. So shared socio-economic pathways in the IPCC 6th assessment will help to address this. So for the perturbed parameter ensemble of HADGEM3 that we're using for the UKCP regional, we're using the RCP 8.5 scenario. It was initially intended as a high-end baseline scenario, but it's been portrayed as a business as usual scenario for many years, as we did track it quite closely for some years. Although current policies would take us to a much lower level of warming. The figure here shows the global impacts for different policy choices. So RCP 8.5 is likely to lead to between 2.6 and 4.8 degrees of global warming. But regionally, climate impacts will of course vary and will be much more severe in some places. So using the regional projections, we're able to look relatively local scale in the UK. For each resolution, 12 kilometre and 2.2 kilometre, we have a 12-member perturbed parameter ensemble. So each model's parameters are plausible but different, leading to different projections, and this encompasses some model uncertainty. So although the ensemble uses only one model, so we're looking at multi-decadal changes in hazards out to 2080. So beyond 2050, we do expect emissions forcing, therefore, to be having a big impact on projections. So as regional modelling programmes do produce other regional models over similar areas in the future, well, there's opportunities that we'll be able to test this more locally. Or at a UK average spatial resolution, we have much more options for large model ensembles that we can use to provide wider context. So where possible through this project, we aim to provide comparisons to other available models. So we here show some examples of compound events using the framework of Schleicher et al., which is currently in press to be released this month. First, we consider the case with multiple variables. For this, we're going to show an example of heat stress in livestock. Then we're going to consider a preconditioning compound event, where a previous event involving one climate hazard means the impact from another later climate hazard is magnified and becomes extreme in terms of impact. So for this, we discuss seasonal changes and the impact of agricultural food stocks. So the large potential spatial event of such events also increases their impact. So I'm considering them also a spatially compound type of event. If this isn't related to agriculture, and I'm not going to show any detail on this one today, but a temporally UK compound event where the same hazard repeats over time is of course the destruction of the railway in the southwest of England. So we had repeated storm surges over the winter of 2014-15, which eventually caused the wall to collapse, but the final surge was not the greatest one. So for our first example of our results in 2018, we've had a very hot, dry summer. So we can see here the temperature and rainfall anomalies compared to climatology. In general, wheat yield was down due to the climate conditions. And of course, that means you know, when it's very hot and dry, you have to spend a lot of money to water crops to try and mitigate the impacts. The conditions were particularly exceptional because they were so widespread spatially. If there's a deficit in agricultural yield within a country, then additional imports can often make up that deficit. But if climatic conditions for the import countries suffer extremes as well, then that can increase the severity of the impacts. So the hot, dry summer of 2018 was preceded by a cold, wet spring. This meant that livestock were kept inside for longer and they have to be fed. So when the weather's good enough in spring, cows are put outside where they can eat the grass. However, in a quick transition to hot summer conditions, the quality of the grass deteriorates and livestock are put under heat stress. So in 2018, the cattle in many parts of the country had to be brought back indoors and needed feeding for much of the year. So this meant that livestock feed was in limited supply in parts of the country. In addition, being inside and not eating fresh grass for much of the year can expose cattle to health risks. So to consider the problem of the cold spring followed by the warm summer, here I'm assuming spring, which I define as February, March and April, and consider if the UK monthly average for each of these months is less than the criteria for the cold spring months in 2018, so a certain amount below climatology. So I do the equivalent for the warm summer months of May, June, July. So for just one ensemble member, I'm here showing for illustrative purposes when cold spring and warm summer events occur in the projection. So if there's one cold month in the spring, there's an index of 1, 2 cold months, an index of 2, etc. As you probably guess, there's fewer instances of cold springs further into the future, but hot summers become common. So I'll just add that all the results that I'm showing here today are preliminary results using raw model data and they're not bias corrected. So we calculate the probabilities over 10-year periods of both the cold spring month and a warm summer month happening in the same year, and show these as a spread across all members of the ensemble. So we can see that between 2020 and 2040, one cold and one warm month may happen up to 3 times in 10 years. So events are slightly less severe in terms of duration than 2018, and there's something that may need to be prepared for. Events similar to 2018 in terms of magnitude and duration may be up to a 1 in 10 year event between 2020 and 2040. And we don't see any instances of 3 cold spring months and 3 warm in the regional ensemble. So to look at a different daily timescale case study, we're here showing an example of thermal heat stress on livestock. So this index includes temperature and relative humidity information. So we consider this a multivariate event. Some heat stress decreases the weight gain, fertility and milk yield of dairy cattle. And obviously extreme heat stress could lead to mortality. So we here show the results using a more moderate threshold for heat stress for dairy cattle for the southwest of England, where the headquarters of the Met Office are. So in the southwest, we have over 1.7 million cows. So this is an area highly vulnerable to this hazard. So for each of the ensemble members, we show how many days per year are above a threshold for heat stress in a baseline climate period of 1981 to 2000, so in blue, and the future climate period of 2061 to 2080 in red. So as you can see for all of the ensemble members, there's a big difference between the days above the threshold in the baseline period, so you might just have a handful per year, and in the future periods where there may be up to 2 months each summer where livestock are stressed. So there are differences between each ensemble member. So this reveals the uncertainty that's associated with parameterizations in climate projections. So we can consider how this links with the previous case study we talked about, where hot summers mean that livestock may need to be kept indoors and fed additional hay or silage. So this require more crop availability for that purpose.
2 minutes left, Freya.
Thank you. So just to say a few words about our future steps. So through the lifetime of the Strategic Priority Fund for Climate Resilience, we'll be extending these case studies, and we have some other agricultural studies we're working on, and we want to develop case studies in other sectors, including by further developing our links across stakeholder communities. So please do get in touch if you would be interested in exploring future collaboration. Eventually our methodologies will be published and the software made available for others to use. So to summarise, we're combining understanding of future hazards in the UK with exposure and vulnerability information to try and understand risk to UK sectors. So we're using case studies here, and today I've shown some examples we've been working on initially. And we also aim to include some advanced statistical methodologies in the future as well. So our approach is dependent on building links with stakeholders, and our intention is that our research can be fed into decision making for UK climate adaptation. So thank you, and I'll pass back to Kate now.